Okay, so now we can actually write the general form of a permutation in using factorials. Okay, so let's say we have n people in a group, and then we need to select r of them. Okay, so first we have n ways to select the first person out of the r people. Then we have n minus 1 people to select the next person out of the r people. Then we have n minus 2 people to select for the next person in the group of r. And then we finally have only, and then for the final rth position, we have n minus r plus 1 people who can be that position. So then, therefore, the permutation of n comma r is equal to n times n minus 1 up till n minus r plus 1. Okay, we can also write this in a more clean way because this way it's honestly kind of messy. If you notice this multiplication is just n factorial without the terms from n minus r minus 1 all the way back to 1. So because of this logic, p and r is also n factorial divided by n minus r factorial. Do you understand this? Do you understand why these two products are essentially the exact same thing? Okay, I'll take that as a yes. Okay. So that was the general form of a permutation. Now we can do something pretty similar called combinations. So a combination is basically a permutation, but then order does not matter. In permutations, the order of who we selected first and who we selected second, the order did matter, but in combination, the order does not matter. So our first example in a permutation was the number of ways to select 3 officers from a club of 10 people. A similar combination will be the number of ways to select a committee of 3 people from a club of 10 people. Okay? Because in a committee, the order does not matter. So let's say if 3 people in the committee are A, B, and C. Choosing A for the committee first, then B, then C, that's the exact same committee as picking first B, then A, then C. So when we're counting permutations, the order of what we do, that does not matter. But then when we were choosing the officers, the order of who we picked did matter because each position was different. But then in a committee, everyone is the exact same, so order does not matter. So now, how can we solve this problem? The number of committees of 3 people when we have a club of 10 people. So first, we can just do the normal way. We have 10 people for the first position in the committee, then 9 people for the second position in the committee, and then 8 people for the third position in the committee. But then in this multiplication, we're actually making the mistake of assuming that order matters. Because in this multiplication, order doesn't matter of who we pick first, who we pick second, and who we pick third. Okay? So this is why we actually have to divide to fix our mistake. Each committee, A, comma, B, comma, C, it can be arranged 3 factorial ways, right? So each committee is being counted 6 times. That's why we have to divide this multiplication by 3 factorial to get our final answer. So then we have the number of committees is 10 times 9 times 8 divided by 3 factorial, which is equal to 10 times 9 times 8 divided by 6, which is equal to, get a 3 times 2. You can cancel this out over here. 3, 4. Then that's 120. Okay? And you could have also done this the other way, because remember before we had 720 ways to pick the officers, but then in each group of 3 officers, we're counting them 6 times in this. So just divide by 6, then we get 120. There we have it. Okay, so now before we generalized a combination, we generalized a permutation. So now we're going to generalize the combination. Okay. So let's look at forming a committee of R people from a group of N people. Okay. We have N people to select for the first position in the committee, then N minus 2 people for the second position, then so forth until we have N minus R plus 1 people to select for the final rth position in the committee. But we're making a very big mistake here because we're actually overcounting each committee. Because let's say the committee, let's say R is equal to 2, so 2 people in so a committee of 2 people. Then we're counting the committee A comma B twice. We're counting the committee choosing A first and then B, but then we're also counting the committee choosing B first and then A. Both committees are exactly the same, so it doesn't matter who we pick first. But in this multiplication, each committee is being counted several times. So each committee of R people can be arranged R factorial ways. Remember the book example? So that's why we have to divide this multiplication by R factorial to get the number of committees of R people when we have N people. So we actually have some notation for this. We can say first when we're speaking we say N choose R, and then we can write this in the following ways. We can first write as a binomial coefficient like this. This is called binomial coefficient, and it looks kind of like a fraction with parentheses with no line separating the numerator and denominator. It just means N choose R, which is the combination of choosing R people from a committee when we have N people. And then we can also write N choose R as Cn comma R, and we can write this as NCR. The first way will probably be the most common way, but then occasionally you will also see the second and third notations being used. So now let's recall that formula that we created for the generalized permutation N choose R. So this formula, this was just this was N times N minus 1 until N minus R plus 1. Then we divided this by R factorial because each committee was being counted R factorial times, so we had to divide by R factorial to fix this mistake. But then remember, in our generalized permutation, we actually found out that N times N minus 1 up till N minus R plus 1, this is simply N factorial divided by N minus R factorial. So then because of this, we can write N choose R as N factorial divided by N minus R factorial divided by R factorial, which is equal to N factorial divided by N minus R factorial multiplied by R factorial. Okay, I'll write this a little bit more clearly on a blank page. So N choose R, forming a committee of N people from a group of N people, is equal to N factorial divided by the product of N minus R factorial and R factorial. So this class is just part 1 of my combinatorics series. So we're only going to be looking at some basic theory in this one. In the second and third session, we'll look at some more theory and then we'll do more problems. So we're not going to be doing like many advanced problems in this class. So let's look at some direct applications of this formula of N choose R. First of all, the number of ways to choose a committee of 4 people from a group of 6 people, 6 choose 4, is equal to 6 factorial divided by 2 factorial times 4 factorial, which is equal to 6 times 5 divided by 2, which is equal to 15. Does everyone understand this example? Okay, I'll take that as a yes. Let's look at a more like different scenario kind of example. So let's say if we have 20 people in a party, okay, and then each person will shake will shake hands with somebody else, okay. So how many handshakes will be there if every person in the party shakes their hand with every other person in the party only one time? Okay, the answer for this is very simple actually. It is just 20 choose 2. This is because we have 20 people and then we need to see how many groups of 2 people that we can make. And by the definition of a combination, this is just simply 20 choose 2. So we can write this using our notation as 20 factorial divided by 18 factorial multiplied by 2 factorial, which is equal to 20 times 19 divided by 2, which is equal to 190. Does everyone understand this? Okay. Now let's look at one more example. So let's say if we have an octagon, which is a polygon with 8 sides, something like this. Let me try and draw an octagon. Okay. Let's draw an octagon. This very bad drawing is an octagon, a polygon with 8 sides. So how many diagonals does this octagon have? A diagonal is something like this, something like this. Basically, any line connecting 2 points, given that that side lengths are not diagonal. So this over here is not a diagonal, but then this is a diagonal. Okay. So how many diagonals are there? So first we have 8 points on the octagon. 1, 2, 3, 4, 5, 6, 7, 8 points. So we have 8 choose 2 ways to pick. So we have 8 choose 2 lines we can make because each line is defined to have 2 points. So there are 8 choose 2 lines we can make. But wait, we're not done, because in this 8 choose 2, the number of like committees of 2 points that we can have, we are also counting the side length. Like we're counting this, we're counting this, we're counting this, we're counting all of those. And there are 8 side lengths. So then we have to subtract 8 from 8 choose 2. So our final answer is 8 choose 2 minus 8, which is equal to 8 choose 2 is 28. So 28 minus 8 is equal to 20. So an octagon has 20 diagonals. Okay. Now we can look at something called Pascal's Triangle. So this is a triangle. We have ones on the outsides. And then the numbers on the inside, they're the sum of the 2 numbers above it. So this number is 1 plus 1 equals 2. This number is 1 plus 2 equals 3. This number is also 1 plus 2 equals 3. This number is 1 plus 3 equals 4. This number is 3 plus 3 equals 6. This number is 4. Yeah. Then we can let's make another line. Let's make another line. Let's draw another one pretty small over here. Okay. Let's draw a bigger Pascal's triangle. 2, 3, 3, 4, 6, 4, 5, 10, 10, 5. 6, 15, 20, 15. Okay, so this is the first 1, 2, 3, 4, 5, 6, 7 rows of Pascal's triangle. So each member of Pascal's triangle can actually be represented as a combination. So if we let this row over here be row 0, then row 1, row 2, row 3, row 4, row 5, row 6, we can write each element of Pascal's triangle as the following. So we can, so this over here is 0, choose 0. Then the elements in this row are 1, choose 1, are 1, choose 0, and 1, choose 1. And the elements in this row are 2, choose 0, 2, choose 1, and 2, choose 2. These elements are 3, choose 0, 3, choose 1, 3, choose 2, 3, and 3, choose 3. So similarly, for any row n, the elements in row n are n choose 0, n choose 1, n choose 2, all the way up till n choose 3. I mean, all the way up till n choose n. Does everyone understand this? So we can actually get a pretty neat combinatorial identity from this Pascal's triangle. So, start basic Pascal's triangle. So let's say if this element over here, let's say this is n choose r, okay? Since this element over here is one right to the previous element, this element is on the same row n, so it's n choose r plus 1, okay? Then by the definition of Pascal's triangle, this element is the sum of the two numbers above it. But then because each element of Pascal's triangle can be expressed as a combination, this element is actually n plus 1 choose r plus 1. So then, therefore, n choose r plus n choose r plus 1 is equal to n plus 1 choose r plus 1. Choose r plus 1. Swamayam is the TA, and if he wants, he can give some examples for this, like by sharing the screen or something. Hello? Okay, whatever. So let's go through some examples of this. Okay. So first of all, let's say 2 choose 3. Oh, sorry, not 2 choose 3. 4 choose 3 plus 4 choose 4 is equal to 5 choose 4. You can verify this on your own, but it is true by this identity. It's called Pascal's identity because it's formed from Pascal's triangle. So another example, 7 choose 4 plus 7 choose 5 is 8 choose 5. Okay? Yeah, so do you want to give some examples? Okay. I'll just keep going while he's coming. So, we gave a Pascal's triangle proof of this identity, but there's also an algebraic proof of this. So the algebraic proof is as follows. So n choose r is n factorial divided by n minus r factorial times r factorial. Okay? Then n choose r plus 1 is n factorial divided by n minus r minus 1 factorial times r plus 1 factorial. Okay? Then n plus 1 choose r plus 1 is n plus 1 factorial divided by n plus 1 factorial divided by n minus r factorial times r plus 1 factorial. So now you can verify this on your own, multiply this and this, and then soon you're gonna get this. So that's an algebraic proof of this identity. Then we also have a different combinatorial proof of this identity. Okay, so let's say we have n things. Okay, the number of ways to choose r things from this n things is equal to the number of ways of choosing r minus 1 things from n minus 1 things, and then adding this to the number of ways of choosing r thing from n minus 1 things. Okay, so I'll explain this a little bit more clearly. So the number of ways to choose k things to choose r things from here, this is equal to the number of ways. So we can choose r minus 1 things from n minus 1, and then we can add this to the number of ways to choose r from n minus 1, right? So then we can just express these as combinations, equate them, and then we have our basic identity. I'm not going to go further with this because of its trivialness. Okay. Next identity. So now we're going to look at the hockey stick identity. So what it says is that so n plus 1 choose r plus 1 is equal to it's equal to 1 minute. Let me find. It's equal to r choose r plus r plus 1 choose r, so on, keep adding until we have n choose r. So it's saying that n plus 1 choose r plus 1 is n choose r plus n minus 1 choose r plus n minus 2 choose r all the way until r choose r. Okay, so now we can do a proof of this by using Pascal's identity over and over again. So r plus 1 choose r. R choose r. This is the number of ways of selecting a committee from r people when we have a group of r people. This is just simply 1 because there's only one way to select this committee. So then therefore, r choose r is 1, and r plus 1 choose r plus 1 is also 1, because it's the number of ways of choosing a committee of r plus 1 people from a group of r plus 1 people. So like they're the exact same basically. So we can replace r choose r with r plus 1 choose r plus 1. Then Pascal's identity time. So adding this, use Pascal's identity, we get r plus 2 choose r plus 1. Then the next term in this sequence is r plus 2 choose r, Pascal's identity again. Then we get r plus 3 choose r plus 1. Then keep applying Pascal's identity over and over again. Then you're going to get n plus 1 choose r plus 1. So this is known as the hockey stick identity. Okay? So next identity. N choose r is equal to n choose n minus r. So the proof of this algebraically is very trivial, so we're only going to go through the combinatorial proof. So let's say choosing r people from n to be on a committee, it's the exact same as choosing n minus r people to not be on the committee, because for every way that we have those n minus r people to not be on the committee, we have the remaining r people to be on the committee. So they're both counting the exact same thing, which means that they're both equal to one another. Okay. So now we can do something called Vandermonde's identity. So what this says is that the sum so actually we have to first introduce sum notation. So this symbol, it's a capital sigma. It means sum. So and then we have an index at the bottom. So let's say the index can be any variable. We can let's say r equals to 0, and then the top numbers, what we are summing until. This can be, let's say, 5, and then let's say this expression is x squared. And what this means is summing 0 squared plus 1 squared plus 2 squared up till 5 squared. Okay. So now let's look at a couple examples of sums so we can get the hang of this new notation. Let's say the sum I equals 0 all the way from 10. Now let's say n choose r. This is just equal. N choose I. This is equal to n choose 0 plus n choose 1 all the way up till n choose 10. Okay? Everyone understand this notation? It's fine if you don't. I mean, it's fine if you have any questions. Anyone have any questions so far? Okay. So now we can write Vandermonde identity, because this identity, it has some notation. What it says is that summing k equals 0, summing from 0 to r, m choose k times n choose r minus k is equal to this is equal to m plus n choose r. So I'll write this again very neatly. Okay. So we have Vandermonde. What this says is summing k equals 0 up till r, m choose k times n choose r minus k is equal to m plus n choose r. Okay. So now the proof of this is that so let's say we have m boys and r girls. Okay, we need to form a committee of r people. Okay, so then the left side. So think of it this way. Okay, so we can pick k boys, and then if we pick k boys, then we have to pick r minus k girls, because there have to be r people on the committee, right? So then this can be for any case. So we're going to sum over all k because it's counting. Let's say if k is equal to 0, we have 0 boys, then we have r girls. Then let's say if k is equal to 1, we have 1 boy, and then r minus 1 girls. And then we're summing until r, because if there are boys, then we have r minus r equals 0 girls. And then we can also just count this directly by saying we have m plus n total people, and then we're choosing r people. That's the right hand side. So this is why the identity is true, because both sides are counting the exact same thing. Does everyone understand this? Okay. So now let's go through the final, not the second to final thing for today. It's called stars and bars. This is a very common problem in early math competitions. How many ways can you distribute 5 candies among 3 kids? Think about this for a minute. So we have 3 kids. And then we have 5 candies. 1, 2, 3, 4, 5. How many ways can we distribute these 5 candies to these 3 kids? Each candy is the exact same type. So let's say all 5 candies are Hershey bars. And this is person A, this is person B, this is person C. So right now we're gonna use a technique called stars and bars. So we're gonna like try and place dividers among these. So then we have three partitions. The first partition goes to person A, second partition goes to person B, third partition goes to person C. Okay? So this is how we do the partitions. So first we are going to organize those N people and the R people. We have in like let's say sorry, this marker is not working. Give me just 1 minute. Fix this. Okay, yes. So let's go back to our problem of distributing 5 pieces of candies to 3 kids. So we're gonna be placing dividers among this. So how many dividers do we need? So we have 3 partitions. The answer is 2 dividers, because if we put, let's say, a divider here and then a divider here, person A gets this, person B gets this, person C gets this. But then you might be thinking, what if a divider is at the end of the row, like this? Candy 1, candy 2, candy 3, candy 4, candy 5. Then what if a divider is here, here, and here? Then this is what sorry, not there. I mean, let's fix this. Yes, so what this means is that this candy goes here, this candy goes here, this candy goes here. Okay? So similarly, if we have n kids, then we need n minus 1 dividers. So then over here, we'll have a total of let's say we have R candies, we'll have R plus n minus 1 total things, because we have R candies and then n minus 1 dividers. Okay? So this is the total number of elements here. But then how many ways can we arrange this? So we actually have the number of ways to arrange this is equal to n plus R minus 1, choose R. I'll write this again a little bit more clearly. This marker's not working. Yes, so I'm saying that that the number of ways is n plus R minus 1, choose R. This is because we'll have a total of n of R plus n minus 1 things, because we have R candies, n minus 1 dividers, and then that's the row, and then we have to choose where to select the R candies. And this is just simply n plus R minus 1, choose R. So this is the number of ways to distribute R candies to n kids. It's a very, very famous problem and a very common technique that you're going to need. Okay. Final thing for today, binomial theorem. So this is how we can expand a binomial to 1 power. So definition, a binomial is just a sum of 2 things. So x plus 4 is a binomial, y plus 3 is a binomial, so forth, so forth. Let's say like 2 plus k is the binomial again. So the binomial theorem is going to help us expand things such as x plus 2 to the power 5. So then we're not going to have to like write this all out and then like spend 30 minutes solving this calculation. That can be extremely easy with the binomial theorem. Okay, so now let's see how it works. Let's try and evaluate x plus r cubed. So first of all, we're gonna have an x squared, right? Because when we have, let's say, 3x plus r's that we're multiplying, we're going to have an x cubed. But then how many x cubes will we have? The only way to get an x cubed is to take an x from here, an x from here, and an x from here. So we're going to have 1 x cubed. Okay? Then, how many x squared are we going to have? How many are x squared? So we get an x squared by taking 2 x's and then 1 r. Okay? So then there so then we have 3 choose 1 ways to make an x squared. Okay, because we have 1 r in each, and we have to select 1 r from the 3 r's. So then remember, in each x squared we're going to have an r. So the answer to this is going to be 3 choose 3 choose 1 times r times x squared. Then how many x's? To get an x, we're going to have an x, then an r, and an r. So an xr squared. Okay? So there are going to be 3 choose 2 ways to select the 2 r's that we're going to use. Then we're going to have an x and then an r squared. Then similarly for the final term, we're going to have just an r squared, just an r cubed, because there's only 1 r cubed that we can make. Okay? Now we can just generalize this theorem. It's called the Binomial Theorem. So it says that n plus k to the power x is equal to x choose 0, n to the power x, k to the power 0 plus x choose 1 times n to the power 1 n to the power x minus 1, k to the power 1, and then keep adding until we're going to have x choose x times x to the power 0, k to the power x. So we can actually write this in sum notation as we did before. We can write this as the sum of, we'll write this as k is let's use the variable r equals 0. We're summing from r0 to x of x choose r. Then we have then we're gonna have n choose x minus r, and then k to the power r. Because if you look at this, each of these terms satisfies the sum, and the proof of this is because that we let's say, how many k's can we make? We have x choose 0 k's, so we have that many n to the power x. Then how many n to the power x minus 1s do we have? So in these, we're going to have x minus 1 n's and 1 k. So we have x choose 1 ways to select the k that we're going to be using. Similarly, let's say if we want to have n to the power r, then we're going to have k to the power x minus r, because we're going to have the remaining k's. And then we're going to have x choose x minus r, because this is the number of ways to select the k's that we're going to need. Does everyone understand this theorem? So we're going to be looking at like some more examples with these with these identities, and some other problems and some other theorems that can be pretty useful. Thank you all for coming.